Welcome to the lesson on 13.3, the base E. Oops, the essential question here is wrong. So we're going to be learning about base E, natural number E, and the implication that it has. Okay, guys. Before we start that, let's just plug in this value over here. And could you pause the video quickly and fill it in for me? If you did what I asked you to do, you would have gotten these answers right here. And this you would not be able to do, but what you would have noticed is that as the x goes to the infinity, it seems to be approaching number 2.718, and then it really slows down over here. Well, that number that it's approaching is called E. As x goes to infinity, f of x approaches the value called E, and this E is called a natural number. And in this, using Desmos, I plugged in the first couple, and then I decided to add in x equal to 2, just to see how the curvature goes. But if you notice, it's approaching this value really, really quickly, and that value is y equal to E, and that's approximately 2.7182818284590, and it goes on forever. It's probably the second most famous number after pi. Okay, this shows up everywhere in mathematics. Now that we know what E is equal to, you see E is just a number, some number that's about 2.718. Let's plug in these values and see what happens. And then if you plugged it in, all the numbers should come out to this, right? Let's plot this and see what it looks like. Right, so e to the x, and it should look a lot like, oh, by the way, the ones in the orange, I decided to add those two because that just wasn't enough. So why don't you go ahead and make a couple more columns for x equal to -2 and -5. I think that gives you a better picture. When you connect them all, that's what that looks like. So this looks like any of the previous exponential growth function whose base is greater than 1. Higher the value of the base, the faster this curve rises. So well, just like before, the domain is all real numbers, and my range is y is greater than 0. Remember, f of x equal to 2 is equal to e to the x is a parent function, parent graph for this type. And we will do some transformations in a little while. And this function, as you could see from left to right, is increasing. My y-intercept is 1. That is because to find y-intercept, x must be 0. And what are the reference points? It's a 0, 0, and 1e. In the past, we had used 0, 0. Plug in 0 into the function or 1 into the function. So that e is actually the base. So in this graph, it's those two, and that represents 2.718. Okay, guys, what's the behavior? As x goes to infinity, y increases to infinity, and as x goes to -infinity, y seems to be going to 0. Okay, very, very familiar, right? Let's move on. The transformation is exactly the same thing, right? The first reference point, as before, except e is the base b. And then we will put h, because that's been shifted, and then we would shift that 1 as well. So you will plug in 1 plus h into the function. And I actually do not spend my time memorizing this. I just do it. I just plug in the values and never had an issue. And then asymptote, that should be a horizontal asymptote. And that's been shifted as well, a vertical shift that is. So that is y equal to k. Okay, let's move on. So here, let's graph this. Pause the video and why don't you try? Okay, guys, we're back. So we notice that the a is equal to 2, and hk is -1, -3, and here are the respective effects. So here, it's positive, a is positive, so there is no reflection, but it is bigger than 0, the magnitude that is. The absolute value is greater than 1, so it's a vertical stretch by a factor of, you guessed it, 2. and that represents translation left by 1 and vertical translation down by 3. I actually prefer to do the transformation using the translations first. And I think of it as the new origin. You could call it NPR, new point of reference. And from here, I would have drawn y is e to the x, but we have a vertical stretch. So instead of crossing at 1 here, it will cross at 2. So instead of crossing at e, which is 2.7, it will cross at 5.4. That's 1, 2, 3, 4, 5.4. It should be about there. Okay, let's just plot the points, see what happens. Okay, I missed it by a tiny bit. Here you go. And then we connect those 2 points. And there you go. And these are the reference points that I had used. But you could use this to confirm your answer. But I still prefer to do the translations, translate the HK, and then do stretches. Okay, and I like to do both ways so that when you're done, if they both agree, then I know I did it correctly. Okay, guys, why don't you take a little time and give it your best first. Okay, we're back. So we know that the first reference point that we give, the one that is closest to the horizontal asymptote, is in fact the h. So I know that already. And k, as you can see, that was given to you to be 3. I know that my base is 2. But geometrically speaking, we had learned that the gap between this point, the first reference point, and the horizontal asymptote is the a. So we know that a is 2. But I always like to double check because I might be mistaken. So algebraically speaking, we simply plug in the fact that f of 2 is 5. So we have this equation right here, guys, right? So I plugged in the hk. H is 2 and k is 3. And then I'm looking for a. And then x is 2, so I put 2 over here, guys. Then when I solve for that, e to the 2 minus 2 is 0. Therefore, it is 1. Solving for a is 2. So I'm pretty sure that this is correct because I got the same answer doing 2 different ways. So we're going to be modeling with the exponential growth function, and we know that the base e is about 2.718. And if you have a function like this, where c is a positive, let's talk about an example here. Okay, Dow Jones Index is a stock market index for the New York Stock Exchange, and the Dow Jones Index for the period of 1980 to 2000 could be modeled by this equation, where t is the number of years after 1980. So how long would it take after 1980 to reach 3000? We've done this before, right? So what you would do in y1 is enter that equation, and then in y2 the value that you want to reach, right? And then when you graph them, this is what we get. Now when you do that, you have to set your windows carefully, right? And I like to see some, left hand side of the y-axis. I like to put some -3 or -5. I sort of guess that it probably shouldn't take more than 15 years, maybe 20. So I plug it in. If it's way off base, you could just always go back. And I like to just have some room for at the bottom here. So how did I choose the maximum value? Well, we're interested in 3000. I also like to have some room on the top. So I just added a couple thousand. And that was it. I mean, I don't have any secret, anything other than that. I have just a couple of guidelines. I just like to see a complete picture. And then I've shown you how to find the intersection of two curves, two equations. And when you did that, as you could see right there, comes out to 10.15. So my answer is it took 10.15 years after 1980 for Dow Jones Index to reach 3000. Okay, be sure to bring your TI calculator so we could practice more in class. Alright guys, have a good night.